Today's episode is brought to you by engineering.com, a globally trusted source for engineering content. Check out this and many other exclusive videos for the engineering professional found only on engineering.com TV today.
Launching payloads into orbit has always been difficult. As a species, we've only been doing it for 65 years, and it's always been expensive and difficult. Now, one of the reasons why it's so expensive is because they need to use composite rockets consisting of two or more separate rockets stacked together as stages, dropping off the lower stages as the assembly accelerates to the over 17,000 miles an hour needed to sustain Earth orbit. Now, have you ever wondered why we can't just build one giant rocket with powerful engines and just blast the entire thing straight into orbit? Well, the answer is found in a remarkably simple mathematics called the rocket equation. Now, this was derived by the Russian Konstantin Tsiolkovsky at the turn of the last century, decades before spaceflight was even close to a practical reality, so this was developed from first principles, not empirically. It's rooted in the basic equations of Newtonian physics, and it's immutable. Now, the key thing to notice about the rocket equation is that the velocity term on the left, which is the speed needed to reach orbit, is solely dependent on two variables on the right: engine exhaust gas velocity and the ratio of the full to empty weight of the rocket. Now, engineers call this the mass fraction, and structurally this is the core of the single stage to orbit problem. The velocity needed to attain orbit is naturally a constant, and exhaust gas velocity available through the combustion of chemical rockets, well, that tops out at something a little less than 3 miles per second, about 6,500 miles per hour. Now, I'll spare you the mathematics, but with a fixed exhaust gas velocity and a known orbital velocity requirement, the mass fraction needed for a single stage to orbit could be as high as 40 to 1. And since the only way single-stage to orbit rockets can reduce their mass in flight is to consume propellant, very little of the launch weight of the vehicle can be made up of engines, tanks, and airframe. Structure is heavy, and there's just no way around this problem. So to solve it, as the rocket lifts off and flies, its mass has to drop by more than just the weight of consumed propellant and oxidizer, and that's why rockets are built in stages. So dropping off the dead weight of empty tanks, airframe, and engines allows the now smaller rocket to ignite and start its part of the journey not only higher, but faster, lowering the necessary delta V to reach orbital speed. Now, 2 stages are common, but as many as 4 have been used for satellite launch. But is there any way to get around this seemingly impossible restriction on single stage to orbit? Well, possibly, but it will take some engineering. A British company called Reaction Engines is building a new type of power plant that uses a combined cycle, a novel air-breathing ramjet that transforms into a rocket once the aircraft has reached high altitude and hypersonic speed to continue its journey into space. Now, with advanced materials and high-performance propellants like liquid hydrogen, it's theoretically possible to achieve single-stage to orbit, but to do so carrying any useful payload is doubtful. Now, has anyone come close? Well, yes, ironically a long time ago. In December of 1958, a test version of the Atlas ICBM was launched into orbit, carrying a recorded Christmas greeting from then-President Dwight Eisenhower. Now, the Atlas was considered a 1.5-stage rocket because it dropped 2 of its 3 engines in flight, but achieved orbit with the launch tankage and airframe. Now, even then, to pull off a mass fraction that works with the rocket equation, the engineers that designed it at Convair had to eliminate the conventional rigid airframe construction and build the Atlas out of paper-thin stainless steel inflated with nitrogen gas like a giant balloon. Now, this expensive and difficult-to-handle technology resulted in a rocket with a mass fraction of a little over 20, a figure that has not been improved on today. Atlas would go on to a long and storied history as the launcher for John Glenn and the Mercury astronauts, as well as interplanetary space probes. But to lift any real weight into orbit, it needs a second stage. Propulsion is a problem. Nuclear rockets, well, they could be a solution, but there are obvious drawbacks to flying nuclear reactors. The reaction engine's hybrid engine approach looks promising, but it's been decades in development. And I doubt that airframes and tankage can get much lighter than they are right now. So does this mean that we're never going to board a space liner and fly into orbit like Kubrick's 2001: A Space Odyssey? Well, not with chemical rockets, but maybe with hybrids. I mean, hybrids are the hottest thing in the automotive industry right now, so why not rockets?
Well, that's it for today's episode of End of the Line, brought to you by engineering.com. If you like this show, be sure to subscribe to our channel and click on the notification bell for our next episode. For our deeper engineering video series for the manufacturing professional, visit engineering.com TV to watch exclusive shows like Manufacturing the Future, not found here on our YouTube channel. The link is in the description below. Thanks for watching.